So next talk is from Bernhard Mistlberger from SLAC about the LHC cross-sections at NQ below. Please, Bernhard.
All right. Yeah, thanks a lot for the introduction. Thanks a lot for the invitation. It's a pleasure to talk about some recent projects of mine that I did together with my friends Claude, Falco, Robert, and Julien. And this is based on a bunch of papers that are listed here, and there are a couple more that are going to come out on similar topics. But yeah, let's just get into that. What I'll talk about here today are cross-sections that are calculated for the LHC, for LHC processes at very high order and perturbation theory. So in order for this kind of calculations or for this kind of phenomenology to be relevant, we need to look at a certain set of observables. And these observables are so-called precision observables, and they're characterized typically by having very clean final states, are typically at very large invariant mass, so a lot of energy in the detector that you can actually see quite clearly. And they have to have sizable cross-sections with respect to, let's say, the full LHC data set. So, the amount of data that will be collected by the year 2035. And one paratypical example is the one that I'm showing on the right here. This is the shape of the rapidity distribution of Drelian production. So the production cross-section for 2 leptons in the final state, and normalized to its total cross-section, such that you really only worry about the shape. And what you see here is really the uncertainty on the cross-section that we can measure at the LHC. And this is the 1% mark here. So you see that for a large range of rapidities of observable range, we can actually observe this cross-section to the level of a couple of per mil. So this is astoundingly precise, more than theory can do. This is really, in terms of precision cross-section, this is really the one of the shining examples that we can measure at the LHC. But there are many of these cross-sections or observables of this type that are very interesting. They allow us to test in the end how well we understand QCD or how well we understand LHC phenomenology. It allows us also to test how well we understand detectors. They allow us to test how well we understand the contents of the protons in terms of the particle distribution functions and so on. And the Drelian production cross-section kill is one example of those. Precision observables play then, of course, also a role in our efforts to constrain beyond the standard model physics, for example, via the measurement of the mass of the W boson that we can determine to quite precise levels. If we determine that quantity, we can test fundamental relations of the standard model of particle physics like this between different Lagrangian parameters. And we can see if we actually understand what we are doing here by doing this kind of precision tests. Another example is the measurement of sine theta weak that will be the most precise single determination of this quantity, but at least according to this paper by the Atlas detector in the future. So there are many things that we can get out of precision measurements. Another example is the measurement of Higgs boson properties. For example, the total cross-section to produce a Higgs boson at the LHC. Sorry, I lost my cursor. Is going to be measured to a level better than 2.5% at the end of the lifetime of the LHC. In the end, Higgs measurements will allow us to extract coupling constants. The spectra or the distributions of the Higgs will tell us about the nature of the boson in terms of its CP structure and so on. So there's many things to get out of precision measurements that we want to do, and we want to complement this in order to really see if we understand what we are doing by theoretical predictions. The theoretical predictions we're determining from the framework of general factorization and of the standard model of particle physics, in the sense that we were relating this hadronic cross-sections that we are measuring at the LHC to partonic cross-sections that we calculate from first principle from Lagrangians using this factorization formula that splits long-range and short-range physics into different parts, into parton distribution functions, and the sigma hats here that we can actually calculate perturbatively. For the rest of my talk, I'm really only going to look into QCD perturbation theory. In the end, the strong coupling constant is the largest of all our small expansion parameters, roughly 0.1. And the way this perturbative expansion, of course, works then is that we write down a leading order term plus alpha s times the next to leading order term plus alpha s squared times the next to leading order term. And the one that I want to focus on today is this n cubed or alpha s cubed times an n cubed term. And we're going to see how well this actually works and what we can do phenomenologically at this order. Now, just to give a little bit of an overview of the status of this kind of calculations, this line that you see here is essentially a timeline, and the different dots that are associated with the timeline are just papers that came out for the prediction of production cross sections at the LHC. And you see this timeline here at next to leading order starts at in 1990, and then it ramps up over quite a couple of years. But in the last a decade or so, there was really an explosion of results that came out, and actually this timeline ends here on this particular slide in 2018. But of course, the progress continued, and many more predictions came out since then. But you see that next to leading order predictions are a fairly well-established field, and we can do already many predictions for that. However, this is still not the end of it. I think Simon in the next talk will actually talk quite a bit of how we extend this further, how we go further next to leading order predictions, what the obstacles currently are, and so on. And cube-to-low is a much younger field, in the sense that the first prediction for an LHC cross-section we made in 2015. And ever since, there were a couple of results that came out every year. And this is ramping up as well. So we're getting better and faster in making predictions. We're getting more differential, more descriptive in what we can actually do with cube-to-low predictions. But it's still ramping up. The first result that we had was a prediction for the production cross-section of the Higgs, so the answer to the question of how many Higgs bosons we are simply producing at the LHC. And this is the quantity that I'm plotting here on the right. This is the cross-section as a function of the collider energy, and different bands correspond to different orders in which I truncate the perturbative expansion. Green is leading order, yellow next to leading order, blue next to next, and red cube-to-low. And what we're seeing essentially is that adding this cube-to-low corrections really stabilize the perturbative expansion, in the sense that the red predictions now are contained within the blue predictions, and we see some sort of really perturbative behavior that was, a long time elusive for this particular production cross section of the Higgs boson, a famous example where we actually need to go very high in order to achieve precision. And we also saw that in cube-to-low predictions in the end reduced the perturbative uncertainty, the remaining perturbative uncertainty, quite a bit. In terms of Higgs boson phenomenology, this is really something that was very useful. So if you look, for example, at the quantity, the ratio of the observed cross-section to the standard model cross-section, we see that we constrain this ratio at ATLAS or the CMS experiment at the level of, let's say, ±7% at the moment. And it's in remarkable agreement with the standard model prediction, meaning that we really can test to the level of 7% now if there are deviations from the standard model, and can rule them out at the moment. An interesting side comment is that theoretically uncertainties are already now at the level of experimental uncertainties. So we have to probably think a lot harder in order to move forward in the next decade or so in terms of LHC phenomenology. More generally, the structure of this Higgs boson cross-section follows a similar structure as many cross-sections at the LHC. In particular, we can draw diagrams, schematic diagrams like this here now, for the general production of an electroweak colorless final state product. In the end, this works in the way that we are having this two protons scattering. They emit the two partons, and the partons fuse in a hard scattering interaction and produce the electroweak final state that we might think about. This this final state then might propagate, or its propagation might be described by a Bright-Wigner distribution, and then finally, after a very short time, this final state actually decays into observable final state products. As I said, a large range of processes is described by the schematic that I drew here. In terms of what examples are virtual photon production, the production cross-section of a W, of a Z boson, the Higgs we already had, the Higgs boson and gluon fusion. You can also think about pseudoscalars, gravitons. You can think about associated production cross-sections, and so on. In the end, what's important is that the structure that you have to calculate cross-sections like that is similar to all of them, in the sense that you can use the same techniques, the same tools to calculate analytic cross-sections, partonic cross-sections for these processes. And a lot of the components for them are actually quite reusable, in the sense that integration by part identities might be similar. The integrals, the master integrals that you have to calculate for these processes will be identical. Large pieces of computer code you can actually recycle and use again. So we embarked on a process over the past couple of years of deriving cross-sections for several of these examples, and I want to show you examples beyond the Higgs boson today that we calculated. Right. In the end, what we're using in this framework is that it's fine to essentially calculate the final state product that we are producing because the widths of the particles that we are producing in the middle are narrow. This allows this factorization in terms of a production cross-section and the decay matrix element, and we're going to model the propagation between the two using a Bright-Wigner distribution. I can cast this into a very concrete formula where essentially this formula describes the inclusive cross-section to produce the final state that we are interested in as a function of Q squared, so the virtuality of this final state products that we're producing at the LHC and that we can observe. And it's factorizing it into this production cross-section here in the after the equal sign, then a decay matrix element and the Bright-Wigner distribution. Let's start with the Drellian production cross-section. So really the process to produce any plus and minus pair at the LHC, as I mentioned earlier, one of the standard candle processes, and it's very important for the constraint of partial distribution functions as well. In the end, there are two contributions to the two distinct contributions to the standard model Drellian cross section. One is via the exchange of a virtual photon. One is via the exchange of a virtual Z boson, where you go from the initial state QQ bar pair to the final state lepton pair. The photon contribution we calculated 1.5 years ago, and then you can ask, okay, why is the Z boson more difficult than the photon? And the reason really is that for the photon you only have a vector contribution, and for the Z boson you also have an axial vector contribution, and calculating anything with an axial vector contribution in the standard model always gives you a little bit headaches, because in the end there's this long solved problem of how you treat gamma 5 in dimensional regularization, but it still makes it quite difficult if you want to do high loop calculations to actually operate with that. There are many schemes of what you can do with gamma 5 if you want to do high loop order calculations. Toft and Weltman gave us one scheme. There's another scheme that is was given by Larin, where he says, okay, let's just take the product of gamma 5 and gamma mu and just antisymmetrize it, and what you get is an epsilon tensor dotted into 3 gamma matrices. And the problem really is the fact that there's this epsilon tensor here, and an epsilon tensor is a fundamentally 4-dimensional object. If you work in dimensional regularization, you have to somehow reconcile that and figure out what you want to do with that. The way we deal, or the Larin scheme deals with it, is that essentially we understand this scalar product, this dot product between the epsilon tensor and the gamma matrices as a projection onto a 4-dimensional space. But we can essentially just drag this epsilon tensor completely in front of our cross-section calculation, and do all our renormalization procedure, all our dimensional regularization under an integral sign. And then, once we're done with our calculation, we essentially can contract with an epsilon tensor and figure out what the finite cross-sections actually are. Now, okay, without going too much into the details here, the question is, where is this actually relevant? Where do we actually need to pay attention to this? There are certain diagrams, like the one that I'm showing on the top here, where it really doesn't matter, where gamma 5 really isn't that big of a deal, in the sense that there are contributions like this diagram where the axial vector current can couple to the same quark line twice. And then, it's you all know, if you have gamma 5 matrices, that in 4 dimensions, if you would treat them in 4 dimensions, you could just anti-commute them with all the other gamma matrices, and eventually they find another gamma 5 matrix, and they just would square and give you unity, and the entire problem would disappear. So from this simple, analogy, you would basically see that, okay, this gamma 5 simply has to drop out, and the axial vector squared contribution just really should look like the vector squared contribution. So everything you see from here is something you can identically take from for the Z boson from the photon calculation. But there are these other diagrams that make your life a little bit more complicated, where you have essentially the axial vector coupling to a triangle loop only once, like the ones that I'm showing here, or to a fermion loop only once, like the ones that I'm showing here in the bottom. And of course, this sub diagram that you see on the left-hand side here, where the axial vector couples to the triangle, the fermion triangle. This is nothing but an embedding of the famous anomaly triangle. And of course, there you need to pay attention what your regularization scheme is actually doing, and this is where it gets a little bit tricky. For this particular Lorentz scheme, this means that you will have to regulate UV divergences that are absent, so that are present, that are anomalous, because we are working in 5-flavor QCD, and you have to somehow include the effect of top quark effects that you're neglecting in order to get anomaly constellation right. And you have to make sure that the scheme is not modifying your physical prediction. In this particular scheme, we have to introduce a finite renormalization counter term that is a little bit tricky in order to get our results right. But okay, you can do all that, you can figure it out. And after a while of working through that, we are now able to make predictions for the inclusive cross-section to produce lepton pairs at the LHC. So this is what I'm showing you here. It's the cross-section as a function of the virtuality of the plus and minus pair. This plot is, just to show you the Z peak. In principle, you could see the different orders, but okay, this is not for scale. We're going to go into the QCD corrections in a second. The one thing you can take away from that is that the bulk of the cross section is, of course, at the very close to the Z boson mass, or at very low Q squares. Right. Now, one thing that is maybe interesting now, since we have now multiple contributions that are coming from photons or from the Z boson, is how much of which contribution actually contributes to the totally plus and minus production cross section. As I said, because you have this interference contributions of boson A interferes with boson B, so photon or Z or vector or axial vector current. I'm showing the decomposition here now in this bottom plot, where the total cross-section, the total n-cubed cross-section is normalized to 1, and the individual contributions are shown in the different lines. For example, the contribution of the photon starts off to be the dominant one, very low Q squares, simply because there's a Q square equal to 0 pole in the cross-section that then falls off, at least perturbatively. And then eventually around the Z boson mass, you see that the axial vector contribution essentially takes over as the complete, gives you the total cross section, and then it falls off again, and it becomes let's say a comparable size more or less. The interference contribution in blue is fairly small, but gives a positive effect above the resonance, and the negative destructive interference below. And the vector squared interaction is essentially, very small, but is always present. Right. Okay. In terms of the QCD corrections that we're getting out of that, they look like this here. I'm showing you here the cross section normalized to the n-cubed predictions that we calculated now as a function again of the invariant mass. Different colors, again, different order, correspond to truncation after different orders. Yellow is next to leading order, blue is next to leading order, and red is n-cubed. And you see that at large Q squares, you have fairly nice behavior in the sense that red is contained in blue, but at low Q squares, we actually see quite sizable K factors. In particular, around the Z boson resonance, we see that the next to leading order bands that are here just derived from scale variation, nothing on top of that, don't actually overlap with n-cubed predictions that we find. For the photon, this came still quite as a surprise to us, but by now we've seen a couple of these cross sections, and it seems to be a universal feature in the sense that we are seeing now that this Strelian K factors are fairly universal and the total E plus E minus K factor is really extremely similar to the just the K factor that we saw when we just investigated the E plus E minus production simply via photon exchange. Right. So of course, it's interesting to investigate where might this large K factors come from, and what could be the source of it. So one question that you could raise is it simply that we chose a particularly unfortunate scale in order to represent our cross section. We have to pick some value, but are there values that would be better suited than others? So what we investigated is how does the cross section vary as a function of the factorization or renormalization scale, and essentially we can't make out that there's any particular scale that would be preferred or would give us a much better description of than another one. So this doesn't seem to be any of the origin. And okay, scale variation, all you see is basically that as you go to higher and higher orders, it goes flatter and becomes more controlled in the end. That's just a systematic offset in the predictions. Right. So another thing that we then investigated is, okay, where might these effects actually come from? And we found something that is quite interesting. In the end, what we did is we decomposed our Young cross sections into different sources, into different elementary building blocks that are not really accessible phenomenologically, but as we are theorists, we can play with them and look at them. We looked at the cross section, the contribution to the cross section that we got from the different initial states. So if we, for example, only look at the quark anti-quark initial state, or if we look at the quark gluon initial state, how much do these initial states contribute to our cross section? And the contribution to the next to next to leading order correction normalized to the total next to leading order correction is what I'm showing you here. This plot is a little bit busy, but in the end, what you see here in red is just the contribution you get at next to leading order from QQ bar. In green, you see quark gluon. And the QQ bar one is negative, the quark gluon one is positive, and is at the order of, let's say, 20 here. And in the end, they cancel down. And of course, the total result is 1. So you see that you have a cancellation at the order by a factor of 20 to 1, essentially. And in comparison to that, this blue band is the scale uncertainty that you get, the scale variation uncertainty that you get at next to leading order. So you see that this cancellation far exceeds even that. So this large cancellation always makes us, of course, a little bit uneasy, because this means that if you just misalign the gluon PDF a little bit compared to the quark PDF, you will get very different phenomenological results and very different K factors. So this seems to be either there's something that the current scheme of partial distributions that we are using, the current linear combination is very sensitive to QCD cancellations, or this is fairly aligned, but this is in principle nothing wrong, but okay, it's something that is a little bit worrying, and it's a little bit worrying. And the same pattern actually continues in the at N-cubed, where we see essentially the same game, but the slightly reduced scale, in the sense that we did the same exercise. We decomposed N-cubed corrections into different partonic initial states, and we see cancellations again, with the difference maybe that now also the gluon channel is contributing quite a bit. So the question is, do we see non-overlapping K factors due to imprecise knowledge of PDFs? There's actually another question that is related to that, and that is the fact that we actually don't have N-cubed PDFs that available at the moment, in the sense that PDFs are determined from experiment. They're determined from experiment by matching perturbative calculations to experimental observation. Currently, all the data that we have is matched using next to leading order cross sections. That is one of the sources why we call them next to leading order PDFs. The other one is that we are using the DGLAB kernels, the evolution kernels of partial distribution functions, currently at the 2-loop level. So in the end, this means that our PDFs are not quite ready yet to do N-cubed phenomenology, and we try to derive uncertainty estimates based on that. So we this plot here on the bottom right shows you an uncertainty estimate of how large the effect could be due to the fact that we don't have encubed-low PDFs available. And you see that this is roughly at the order of, let's say, 2% throughout the entire Q-square range. So this means that we are calculating cross sections here now with, let's say, per mil or several per mil uncertainty, but we still have this missing encubed-low PDF uncertainty, simply due to the fact that we only have next to leading order PDFs that could accommodate the difference in K factors. And it will be interesting to watch it in the future and to investigate that more. The PDFs themselves also have still larger statistical and systematic uncertainties that will have to be constrained better in the future in order to make percent level phenomenology possible. That is what I'm showing in the top plot here. Again, there's an uncertainty of 234% throughout the entire Q-square range.
Bernhard, you only have 5 minutes, including some minutes for questions.
All right, I wanted to talk about the W as well, but I'm running out of time, so I'm going to skip the W, and I just make you aware that we also calculated the Drellian production using a W, and we looked at associated Higgs boson production. The point here is mainly for the purposes of this talk that we can look at many different final states. We can derive actually QCD corrections to a fairly large set of precision observables using the same methodology. And what we are seeing for this Drellian type observables is that the QCD corrections are extremely universal. We see very similar QCD corrections between charge current Drellian and neutral current Drellian cross sections. This is what this slide is showing. You have K factors for W plus production, W minus production, and for, sorry, this is actually now the full Drellian neutral current production, not just the photon. And you see the pictures here look extremely similar. And these QCD corrections are very universal, interestingly. In the end, we have really now an entire list of processes that we have calculated, and the phenomenology that we can take away from that is that encubed-low corrections are at the level of a couple of percent. We studied so far ion fusion, Higgs boson production, bottom quark fusion, Higgs boson production, neutral and charge current Drellian, and associated Higgs boson production. And the fact that they are all of the same size and roughly of the target, of the size of the target position of LHC phenomenology means in the end that we should include them. We should think about how we can calculate them. And in particular, it tells us that we have to think in the future as our data are getting more precise, that these cross sections that we are deriving here, they are very idealized observables. These are inclusive cross sections, inclusive production processes. In the sense that we are really taking a look here at the entire detector and thinking about what is actually going into this process as a whole, and we're not allowing for any kind of selection cuts. And we have to go, if we want to do realistic phenomenology, to something that is much more close to the experimental data, in the sense that we have to allow for cuts, we have to calculate fiducial cross sections in the end, in order to make sure we're not neglecting extrapolation uncertainties and so on. And yeah, I'm gonna stop on this slide.
Hi, Lance. Go ahead
Hi.
with your talk, please.
Thanks for the nice talk, Bernhard. Given all these advances on the N3LO cross sections and the fact that the N3LO kernels are not known yet, can any of the computational techniques be applied to determining the N3LO kernels? Actually, some of them are known, but not all of them.
Yeah, some of them are known as an expansion in those many moments. There are a couple of moments available that it would be quite interesting. I keep saying that to see if we can actually see how some of the moments that we know already would impact the fit of partron distribution functions, or even to do just mock studies of their potential impact. In terms of calculation, yeah, I think so. I think we learned actually quite a bit about the calculation of these kind of inclusive cross sections that are applicable to DRS cross sections. There are the usual problems, let's say, that are associated with for loop calculations, in the sense that they are very hard. But there's a large degree of complexity that goes into doing a QCD for loop calculation. But I think there's a lot of lessons that we learn from doing inclusive in kubedelo that might be applicable to that, and where we can actually make some inroads and do things differently than they were done at the previous order. So it's an interesting thing to think about, for sure.
Juan, please go ahead with your question.
Yeah. Hi, Bernhard. So I have a question about the slides 17, I think. It's about the fraction of the.
Sure.
Yeah, this one. Yeah. So the first question is that the n-cube IO here, is it the n-cube IO coefficient, or is the ratio
No.
for? Okay.
It's a total cross section. Yeah.
It's a total. Okay. Great. Then. Okay, so could you explain a bit more about the gamma 5 that was not included in the previous calculation, and here, so which color would it impact?
So it, of course, in the end, the gamma 5 will contribute only to the axial vector squared contribution. So to the AA means axial vector interfered with axial vector. VV means vector interfered with vector. Axial vector only interferes with itself. You can't have a contribution where you only have one gamma 5 matrix sitting around in your process, simply because for inclusive cross sections you simply don't have enough momenta to dot anything into your epsilon tensor. Essentially, you integrate too many momenta out, you can't actually see that, right? There's nothing you can contract with it. If you have two epsilon tensors, you can contract them with each other, and this will give you some contribution to that. Essentially, the gamma 5 itself will only contribute at next to leading order for the first time. Contribute in the sense that it will give you a matrix element that is different from the vector squared matrix elements. What we saw in the end by, we will study this in more detail in our upcoming paper, but what we saw in the end, just by looking at the K factor, is that the K factor for photon production is remarkably similar to the one with the full set boson in there. So there's hardly any difference in terms of observable differences between the axial vector matrix elements and the vector.
Yeah, well, thanks. Well, I would talk to you in private for more details.
Sure.
Thanks.
Alexander, please unmute yourself. Yes.
Yeah, okay. Thanks, Bernhard, for the nice talk. I wanted to ask about the gamma 5 as well. You mentioned the two schemes, but I didn't get if you actually did the calculations in one of them, or in which one, or in both, and what the discrepancy was. Right. So in principle, there's no discrepancy. You can choose whatever you want. The problem with gamma 5 matrices is that, in the Toth-Wertmann scheme, you introduce 4 gamma matrices in the on top of the gamma mu matrix that you have sitting in the current. So you will have to do with 5 gamma matrices per vertex, and that just makes it in D dimensions very complicated, or very calculationally complex in order to carry out the calculation. Just because you get large fermion traces, everything explodes. Which scheme you choose doesn't in the end matter. What we actually did is we chose the Lorentz scheme, we worked in the scheme, and we validated that what we're doing is giving us the correct results by recomputing the vector current matrix elements, and seeing that in the end, after we do all our renormalization and scheme correction procedure, that we reproduce the vector squared contributions by doing it using the axial vector squared contributions. And then of course we have checks on the matrix elements that are different if you want that are coming from these kind of diagrams on the bottom here, that are really distinct between vector and axial vector current squared contributions, and you get some checks on them by making sure that all your poles cancel and that they follow some consistency checks, and D club is satisfied, and that they match the contributions that you would get from the top quark in the UV and so on.
but yeah, we chose this Laren scheme in order to.
Right. So you chose one, but I guess I just wanted to know if at which, if you could point out the steps in which the difference makes there is a difference, and by which time you're supposed to not have any difference between the schemes.
Right. So at the level of the final cross section, it has the same, right? So there's physics.
Well, I mean, you are truncating the perturbation theory, so there might be a residual.
Excuse me, we are running late. We're already 5 minutes late. I guess we have to cut it off here and go ahead with the next talk. I'm sorry about that, but we're really